So now we're going to look at characteristics of polynomial functions, which is 3.2 in your textbook. Before we start looking at the specific characteristics, I do want to now differentiate what we did in 3.1, differentiate the different kinds of polynomial functions we'll have. There's the odd degree functions and there's even degree functions. Odd degree functions just have a degree that is an odd number, a 1, a 3, a 5, 7, so on and so forth. Whereas the even degree functions are those functions that have a degree that is an even number. Now, in odd degree functions, you can have two different types. You can have a leading coefficient, which is negative, right? You can have the number in front of x is a negative number. You can have the number in front of x be a positive number. For example, in f at x, negative x plus 4, the leading coefficient, or the coefficient of the leading variable, the one that has the highest degree, if it's a negative number, then it's going to start in the positive quadrant, in quadrant 2, and it's going to go down to quadrant 4. It's going to start where the x values are negative and the y values are positive, and it's going to have a downward slope where the x values are positive and y values are negative. So it's going to go down. Whereas in an odd degree function, if you have the leading coefficient is positive, the leading coefficient again is the coefficient in front of the variable with the highest degree. So x to the power of 3 is the largest exponent here. So its coefficient is considered the leading coefficient. So if it's positive, you're starting at the bottom, and you might have other variations in between, but it'll start at the bottom and it'll go up to the top. So as you're going left to right, it will be an upward trajectory. So let's look at the end behaviors now for that. We've already talked about this a little bit. Actually, let me take this off for now. For odd degree functions, the end behaviors, if you have a positive leading coefficient, you'll have one type of end behavior. Negative leading coefficient will have a different kind of end behavior. So the end behavior we know, we start with as x approaches infinity, and as x approaches negative infinity, what will y approach? Right? That's our question. So in a positive leading coefficient, which is starting from the bottom left and going to the top right, as x approaches negative infinity, y approaches negative infinity. And as x approaches, sorry about that, put it in the wrong spot. And as x approaches positive infinity, y will approach positive infinity. So as x approaches positive, y approaches positive. X approaches negative, y approaches negative. That's when you have positive leading coefficients. When you have a negative leading coefficient, it's just been reflected. So you can think of it as a reflection over the x-axis, and now it's going to go down and to the right. So what happens to our end behaviors is that x approaches positive infinity, and as x approaches negative infinity, y will approach the opposite. So now as x approaches positive infinity, y will approach negative infinity. And as x approaches negative infinity, y is going up, as you can see in this graph. As you go to the left, the y values go up. So y will approach positive infinity. That's the end behaviors on an odd degree function. Just keep in mind, odd degree functions, they go from one side to the other. And if at any point you get confused between odd degree and even degree, think always back to the most simplest odd degree function you know, which is a line. Think about the y equals x and the y equals negative x. Whatever the end behaviors are for these two functions, that's exactly what they'll be for any odd degree function, no matter how complex the equation looks. Now what we're going to do is we're going to take a look at even degree functions. These are some examples of even degree functions. As we know, they're either going to open up or opening down. So if we look at our n behaviors for positive leading coefficients, as x approaches infinity and as x approaches negative infinity, for the ones that are opening up, they will both approach the same thing. So y will approach positive infinity. And for the negative leading coefficients, where the the parabolas or the quartic functions are opening down, as x approaches positive and negative infinity, y approaches negative infinity. It's just another way of writing these two separately. For even degree functions, this is for negative leading coefficients. For even degree functions, we know that they have equivalent end behaviors. So on both sides of the graph, they're either both going down or they're both going up. So we can simplify this to say as x approaches positive and negative infinity. We cannot do that for odd degree functions because they have opposite end behaviors. So that's the first characteristic we're going to look at, which is end behavior. We have two more that we're going to go over. So let me get to that now. Okay, so looking at turning points now between odd degree and even degree functions. Before we start, I'm going to review turning points, which we talked about back in 1.3 when we had intervals of increase and decrease. A turning point is where your function goes from increasing to decreasing or from decreasing to increasing. Anywhere the graph turns is considered to be a turning point. Now, for odd degree functions, let's get an understanding of the number of turning points. So I do want to specify here, when we're looking at turning points, this characteristic is looking at the quantity of turning points you can have. So I'll give you an example. In a line, there are no turning points. So 0 turning points. How about in a cubic function? Well, we can have cubic functions that look like this, which again, there are no turning points. But you can also have cubic functions that look like this. Right? There's a cubic function here, which can have 1, 2. It can have 2 turning points. Now, so what we notice now is in a linear function, there's none. So if the degree is 1, there is a possibility of 0 turning points. If the degree is 2, a mistake, if the degree is 3, because the cubic function has a degree of 3, you can have 0 or 2 turning points. What we should then recognize is that for odd degree functions, we can only have an even number of turning points. You can have 0 or 2. If it was to the power of 5, right, you could have 0, 2, or 4 turning points. So, to summarize this, the number of turning points in an odd degree function are going to be either 0, 2, 4, 6, 8. You can only have an even number of turning points, and the maximum number of turning points is going to be n minus 1. So now we know that n minus 1 is a number of turning points, which is the maximum number of turning points. The same thing happens here for even degree functions. The maximum number of turning points would equal to n minus 1. So if I have a function which is, say 3x to the power of 10 minus 8x to the power of 9 plus 4x to the power of 3. This function cannot have more then has a max of 9 turning points. What we need to figure out now is what are the other possibilities. Now, for an odd degree function, there's an even number of turning points. So to figure out the possibilities for an even degree function, we're going to use a little bit of logic. Let's say we have x to the power of 4. Well, if it starts here based on n behaviors, we know it's going to have to end there. Well, what can it have? It has to turn here, so that's 1 turning point, and it can turn down, so that's 2 turning points. But in order to get back here, it will have to turn up again. So 1, 2, 3. 1 turning point would turn it back towards the end behavior it needs to go to. A second turning point would turn it away. So the odd turning point goes back to where it needs to. The even turning point goes away from where you need to go. So for an even degree function, we know the max is n minus 1, and then all the other possibilities would be an even number of turning points. So x to the power 4 could have 1 turning point, or it could have 3 turning points. X to the power of 10 could have 1 turning point, 3 turning points, 5 turning points, 7 turning points, or 9 turning points. Right? And the reason there's so many different options is because, and we'll learn about this a little bit later, but there are so many different ways that even the graph of x to the power 4 could look. X to the power 4, the base function, would just be a wider parabola. But once you start adding some extra transformations in there, like if you add in x cubed and x squared and x to the power of 1 and then a number, you can have a quartic function that now adds in a bit of a w, right? It has 1, 2, 3 turning points. So number of turning points, to summarize, for odd degree and even degree, the maximum number of turning points is found by n minus 1. N is the degree of the function. So n minus 1 gives you the maximum. To find the other possibilities, for odd degree functions, it's all the even numbers less than n minus 1. For even degree functions, it's all the odd numbers less than n minus 1. So 4 was n, so 4 minus 1 is 3. So all the odd numbers less than 3 are possible turning points. We're going to move on now to our last characteristic that we're going to discuss together, which is the number of zeros. Now we're going to look at number of zeros, or the number of roots that exist in odd degree functions. Well, if it's starting in one quadrant and it's going to another quadrant, if it's starting below the y-axis and it's going to the above the y-axis, or if it starts above the y-axis and it has to go down here, the minimum would be 1. And then how many turning points can you have in between? Well, for a cubic function, we have 1. For this function, we have 1, 2, 3, 4, 5. So far, we've only looked at an odd number of roots. But so now what we have to figure out is, can you have an odd degree function with an even number of zeros? We know we can have odd because the minimum is 1. Can we have an even number of turning points? Can I draw a function that starts down here, connects to this one up here, but only has an even number of zeros? So for example, 2. Well, let's go up. Okay, so it has passed here, there's 1. Now I need it to come down here, but only touch it once. So that would be 1, 2. So now we know even number of turning points is an option. Even number of zeros is an option. Odd number of zeros is an option. So the minimum is 1. The max would be n, meaning the degree of the function, and everything is possible for odd degree functions. So for an odd degree function, the smallest amount of zeros is 1. The largest amount of zeros possible is n. And for even degree functions, let's see now if it follows a different pattern. what we're going to do is we're going to try to see if we can make even degree functions that has odd and even number of turning points. And we'll see if, odd and even number of zeros, and we'll see if there is a difference. So the simplest one, which is a parabola, is 1. But can I draw a parabola that has no zeros? That's an example. So we know the minimum is 0. You can have an even degree function that has no roots, that has no zeros. If it starts and ends above the y-axis, then there's no reason for it to cross the x-axis. So now what we're going to look at is maximum. You can have 0, you can have 1. Can I draw one that has 2? Well, let's see. Well, that has 2. Continuing with our experiment, can we draw an even degree function that has 3? Right, so we've gotten 0, we've gotten 1, we've gotten 2. Can I draw one that has 3? Let's have it open. So past here is 1. I need to come back down. 1, 2, 3. So now I see the 3 is an option. So every single number becomes an option. This is a quartic function. It's to the power of 4. So the difference now is how many can you have? For a quartic function, can I draw one with 4? Well, what if I extended it up? And that same graph could now have 4. So very similar to odd degree functions. The maximum amount of zeros is the degree of the function, but the minimum is 0. So for even degree functions, from 0 to n is the number of zeros you can have. For odd degree function, the number of zeros that are possible would be between 1 to n. So it cannot have 0 roots. It needs to have at least one x-intercept. That's a summary of what we're going to be looking at. Obviously, I'd recommend that you go through the textbooks, go into more details, go over the examples in order to make sure that you're properly understanding the materials that we're posting here. And I will continue to provide these lessons for you. I'm now rambling.